Okay, I think we can start. Okay, good morning, good afternoon, good evening for everyone. Okay, my name is Zhong Yiho. I'm a professor from the Chinese University of Hong Kong. I'm also the VP conferences of the IEEE CEDA. Okay, it's my great pleasure to invite Professor Alberto Bosio, okay, to give the virtual dialogue talk today. So before his talk, I would like to introduce him about his bio. Professor Bosio, he received his master degree and PhD degree in computer engineering in the area of digital systems dependability at Politecnico di Torino in Italy in 2003 and 2006, respectively. He is now a full professor at the École Centrale de Lyon Institute of Nanotechnology in France. His research activities are related to the design and test of advanced digital circuits and systems. He played a major role in several major conferences. For example, he will be the program chair of DATE 2026, and he's also the general chair of the DDECS, okay, for this year, okay, and he's a member of IEEE and the vice chair of the European TTTC. Okay, so Alberto, the time is yours. Please start. Yeah, thank you.
Okay, yeah, thank you for the nice introduction. Good morning, good afternoon, good evening, everyone, and thanks for being there for this talk. As you can see, the title is Trustworthy AI, and with a particular emphasis on hardware. So, what is the role of the hardware in the trustworthiness? And so, just before to start, I have to. Okay, can you hear me? Right? Everything is okay from the audio. Yeah. Okay. Just a couple of acknowledgements. So all the work that I will present to you today is basically mainly financed by a national French project related to the artificial intelligence. And also I would like to mention that, yes, my institution is the École Centrale de Lyon, that is one of the universities in Lyon. And in this university, I'm serving as a researcher in the Institute of Nanotechnology de Lyon, that is the research lab associated to this. I also would like to thank CEDA, the Council of Electronic Design Automation, for the opportunity to be a distinguished lead presenter and also to have the opportunity to travel to different conferences to present my work and experience. So just before starting the technical part, some headlines to Lyon, because I think it's important to present where a person comes from. So Lyon is one of the biggest cities in France. So depending on the people you talk about, is the second or the third one. So in this slide, say we are in the third place after Paris and then Marseille. And you can see that is a student city in the sense that you have 150K students. We have a lot of university for, and more than 30 higher education institutes like mine. My institute is one of these higher education institutes. And from the heritage and cultural site is one of the is labeled by the UNESCO. So if you have the opportunity to travel to Europe and in particular to France, and you want to visit us in the lab and take a tour in the city, simply drop me an email. It would be a pleasure to have you and to discuss and to show you the city. Now, as I said to you, my lab, the Institute of Nanotechnology, is a joint research unit. We are about 200 people, more or less, permanent people. And we are divided in 9 research groups, so covering very different fields, so from physics, electronics, chemistry, biology, etc. And clearly, my research group is into the electronic field, and we are in the information technology application area. And specifically, our team, so the electronic one, again covers a lot of different, let's say, abstraction layer. You can see here from the bottom to the top. So we have colleagues working on the micro and nano fabrication. So we have clean room facilities in the lab. We can do characterization of fabricated devices. And with this, we can actually do modeling. We can simulate at very low level. And then we can do circuit and architectural up to the system design. And in the group, basically, my role is in system design, and with a specific emphasis to the dependability of such designs. Great. So now let's jump into the main content of the presentation, so Trustworthy AI. And first of all, I would like to try to identify and to define what is a trustworthy AI. And for this, I have just some couple of examples that I simply bring from let's say, internet, but clearly checking the sources. So the first one, since I came from Europe, is the guideline of the European Commission. And specifically, those are ethics guidelines that somehow try to regulate the trustworthiness of the AI. So as you can see, basically this came from 2019, so it's a work in process, but started in 2019. And basically, you can see that basically there are three main, let's say, characteristics. So trustworthy AI should be lawful, so you have to respect the laws and the regulations, clearly in Europe. Ethical, so you must respect ethical principles. For example, you cannot be biased by a specific characteristic, for example, the gender, etc. And the last one is the robustness. So you must be robust from the technical perspective, also considering the social environment. So, and again, here you have the concept of biases that come back again. So for us, the robustness will be basically the main point that I will develop later on. But before doing that, let's check another definition. So, for example, in US, specifically from companies, so you go for NVIDIA, for example, Trustworthy AI basically is an approach to design AI system that basically focuses on safety and transparency for the user, so for the people that basically interact with the AI. So here the concept is transparency, so people must be aware of what happened, why a given, let's say, outcome is provided by the AI system. And then you have the concept of safety that we will see will be related to the concept of robustness that I just introduced to you before. If we look to another big name, so IBM, for example, Trustworthy AI basically are characteristics that basically specify an AI system. So you must be explainable, fair, interpretable, so and transparent. So again, this follows the transparency that was provided by NVIDIA. And then you have again the term robust, safe, and secure that basically we can put under the chapter of the safety. And all of these, since we talk about AI systems, must be related to the hardware side and the software side. So there are a lot of work about trustworthiness concerning the model itself, the concept of the data, etc. And I will not cover this specific part. I will mainly concentrate on the hardware side. Now, since we talk about safety, so we have the term robustness and security. So it means that there are some threats that we have to consider during clearly the design of the system, but also during the in-field life of the system. So to show you an example, let's consider the case where the application, the final application, is an autonomous car. So basically, this accident can be due to different threats. And one of the threats could be what is defined here, system limitations. So this was a case that that happened in Phoenix, in Arizona, with autonomous vehicle, the Waymo there. And basically, the problem was that a person crossed the road with his bike. So basically, this was something that confused the system, because this specific input was never, let's say, seen, if I can use this term, by the car, and for this reason, basically, the car was unable to take the good reaction. So this is defined, considered as a system limitation, because somehow by design, in this case, because of a training that was not complete, so some data were not basically used for the training, and this is a problem because we cannot have a exhaustive training. So this is something clearly important, but is related mainly on the way you apply the training and the way you select the data for the training, right? Then you have problems because you can force a wrong behavior on your system, and you can have what is under the definition of malicious attacks. And in this specific case, the problem was that attackers carefully modified speed limits panel. And here in this example, they modified the panel in such a way that the car understood 85 instead of 35. So this is a way that we attack the system. The system in this case, from the software point of view, is an object detection or a classifier. And simply we force it to make the wrong decision because we carefully modify the. So again, this is a problem related to the way we implemented the network, the model, from the software side. And the last category, that is the one that I will really consider in the next of the section, is, let's imagine that we have a perfect system, and we make it robust, so we cannot attack it. So even in this very theoretical case, we still have to consider the hardware, because even if from the model point of view, from the software implementation, everything is absolutely 100% perfect, we still have the problem to consider the hardware. And if we have a problem, so a fault affecting the hardware side, we can have actually a wrong behavior from the application side. So this can be clearly seen in this chart, in which basically I still have my autonomous car, and I try to see what happens when something goes wrong in the hardware. So basically, we'll have an hardware fault that is represented by this symbol, and the consequence of this fault can be basically classified in three ways. Either we don't have any, let's say, deviation of the application, so the application was supposed to detect pedestrians, and we still detect the pedestrians, so no impact. And basically, this is something that is good for us because we don't have any deviation. Or we have a very critical situation, this one in the middle, in which because of this fault, the application is not capable anymore of detecting the pedestrians. And this is very critical because in this specific case, the car thinks that it can basically accelerate because there are no obstacles, while it's not the case. And so this is somehow something very, very well known in the dependability community. But one interesting thing is that you may have this last case in which, because of the fault, we have a deviation of the application. So we have something that is not exactly equal to the fault-free execution. But this result is still actually good enough, is still usable, because the goal was to detect pedestrians. So here, okay, we are not able to detect as precisely the pedestrian, because you can see here that we have these dark green boxes that are slightly shifted compared to the light green ones. The light green one is the fault-free execution. So we have a small deviation, but still the pedestrian are detected. So this case is something that is interesting for us because it means that there is somehow a capability of tolerating some faults, and the propagation of those faults will not lead always to a completely unusable result or to be completely masked. So I'm starting to introduce some terms, masked, critical, etc. And we will see later on the meaning of this. Again, masked, so no difference between defaulty and default-free. Safe situation, so we have a deviation, but at the end of the story, we can still use it. And finally, we have a critical situation in which we really cannot trust, we really cannot use the output of this specific system. Now, it is clear that we have this kind of problem, and this kind of problem can be very, let's say, important for autonomous car or more in general safety critical application, in which the consequence of a specific problem can really have dramatic consequences. But even in other applications, we can have dramatic consequences as well. So let's consider this example is about the reliability observation with the Llama 3 model coming from Meta. So this is a LLM model. And basically it was trained. So here we talk about the training. So it was training on this very big cluster, 16K GPU. And the problem is that Meta engineers observed faults. And those faults led to have a certain number of unexpected job interruptions. And those interruptions at the end of the story led off basically 50 days of, let's say, extra delay in order to complete the training. So this is clearly something that will not impact the human being. We don't have any, let's say, human life that is in danger because of this. But from the company point of view, if you have 50 days of delay in the training because of a fault, it means that basically you can lose your market window. Because if to do the training you need 6 months and you lost 50 days or almost 2 more months because of faults, these can be very important for the company. And those unexpected job interactions were confirmed to be caused by hardware issues. And since most of the hardware came from the GPU, GPUs are the largest category of the guilty. Then the problem is that this is still under analysis, so it's really hard to understand what is going wrong, but those are data that are public and you can see. So this is the main problem. You can have variation also from, let's say, the high performance computing side, and this can impact specifically for the training, the duration of your workload. Now, since we talk about hardware faults, where those hardware faults came from, so if we consider a very simplistic, let's say, scheme of the manufacturing, the design and manufacturing flow, we can say that manufacturing defects appear during the manufacturing process, so after the design. So once again, we consider that design has been properly implemented, so there are no bugs. All the verification activities have been already done. So we do the manufacturing process, and during the manufacturing we can have problems. So for example, here we have a missing via. So in this specific transistor, the drain is not connected. So you can understand that because of this, the electrical behavior of the transistor is not the expected one. So you can basically have problems when you go up to the circuit level, problems when you go up to the architectural level, and so on and so on. Now, those defects are usually detected thanks to the testing. So we have at the end of production, the testing phase. So for the faulty, let's say, chip, we simply throw it away. And for the good ones, we use this in our final application, right? Now, the problem is that even if the testing phase declares that a chip is defect-free, we may still have problems in the field. because first of all the electronic devices are ages like us. So you have aging phenomena. So basically the characteristics of the electronic devices will be worse over the time. We can have test escapes. Basically, test is not a perfect step in the manufacturing process. We have some metrics, but the point is that we can still have some weak or very small defect that is not manifested during this time, but maybe because of the aging, this weak defect became observable. So maybe you can have this after a certain amount of time that you use your chip. And finally, you may have problems because the environment that will be basically used by your chip is harsh. So you may have, for example, for avionic or space applications, impacts from neutron radiations, and these can cause perturbations, and those perturbations, once again, will impact the app. Now, we have the source of the problem, and we have to understand how those sources will be basically, let's say, how those defects will impact our AI system. So let's consider that this is our AI system. So we have the hardware side and the software one. So again, the fault impact the technology layer, and then they can be propagated or not up to the circuit architecture. They can be then go up to the software level, and they can reach the application software and lead to failure. Okay, so the clear case is, let's imagine that here you impact a memory cell. You have a wrong value into the memory. If the memory store a variable that is used by the application, basically this wrong value actually is propagated up to the application, and it may, at the end of the story, impact the output, and it can lead to a failure. Or in the other case, if the memory fault impacts a memory cell that corresponds to a location that is not used by a variable, in this case, your application simply continues to work properly. How we can understand this? This is basically what is called dependability evaluation in general, and in this specific presentation is related to the AI systems. So basically, dependable is the quality of being trustworthy and reliable, right? Now, how we can do dependability evaluation? We have to do we have to apply the procedure that is called fault injection. This is very, let's say, very well-known methodology. So you can have a look on this book that is published a little bit more than 20 years ago. But anyway, here you have the main concept. What you have is your system. So for us, it will be the AI system. You have a certain a kind of database of faults that you deliberately inject into the system. So basically, you modify the behavior of the system accordingly to this fault list. You apply a workload into your hardware. The workload is basically the W, so the application. For us is the AI model. And A, the activation, basically is the data that you provide to your input. Then you collect the data, basically the output, and then you have to analyze what happened and to understand at the end of the story if you get masked, critical, or a safe situation. Now, this is very, in principle, simple, but the problem is that it's very costly. So if you look at this example, so those are some numbers coming from a book. And basically here you have the cost where, first of all, the fault injection is done at simulation level. So we simulate the behavior of the model, and we can simulate it at RTL, or at microarchitectural level, or at architectural level, or we can simply run the software. And clearly, the lower the level, the higher the simulation time. And this is without injecting any faults. So if we consider faults, so if we consider that we do the fault injection, basically means that depending on how many faults we inject, 2000, 16,000 faults, the simulation time explodes. So the first consideration here is that I clearly cannot do simulation at RTL level. And if we consider what is the complexity of this specific system that we are simulating, we can see that is a 4 kilobit hardware component, so very small, and we run a benchmark of 50 million of instructions, right? So this is not a complex design. And you can imagine if you transpose these numbers into a GPU that actually execute a given AI model. So evaluation time explodes. If you look at the fault injector specific for AI, here I just put some cases because the literature is very vast. So I put, let's say, the first, let's say, injectors. So by doing some publicity, I would like to cite this work that we did in collaboration with colleagues from Politecnico Torino. This was in 2019. Then the year later, we have the PyTorch fault injection. So those, this one basically exploit PyTorch, which is one of the most used framework for developing DNNs to do the fault injection, and also Tensor fault injector, the same but applied to TensorFlow. That is the other. There are many more. But the problem is that those model based, those fault injectors, sorry, they usually perturbate the model structure. So they mainly work at the software. So they do not consider the hardware that basically deploy the application. And this is a source of problem. So it's really important to consider the hardware because here we did a study this year, published this year, in which basically we consider a very small AI model, LeNet 5, very simple one. And we do the injection by considering tensor FI. So we inject into the memory. So more specifically, we inject into the weights and the other internal, let's say, model variables. And we get these numbers, the green bar. So you can see here that higher the bar, higher the failure rate. So higher the criticality of a specific component. So those are the different layers or components of our network. So, but when we consider the hardware, so we inject into the register of the microcontroller executing this model, you can see that basically the criticality changes. Because, for example, you can see that fully connected to was supposed to be somehow robust, but if you consider it's very, very critical. It's very like the first one. So by injecting the closer to the hardware will lead you a different numbers, different results, and this must be taken into account because it can really change the way you consider the critical components in your network. And clearly, if you know what is critical, you can protect it, and this will be the next part of the presentation. So why it happens that we have different results? So let's just consider a very simple example. So first of all, let me say why we or which kind of hardware we should use. So there are papers that basically do the profile of AI workloads, and the most let's say the most used kernel is the matrix to matrix multiplication, so used almost every time. And basically, matrix to matrix multiplication is a complex operation because basically is a cubic complexity. So hardware design for AI, basically, in our case, the Systolic Array, aims at accelerating the matrix to matrix multiplication. So I don't go to the details, but you can see that a Systolic Array is an array of processing elements. In this case, we have a 3x3 array, and we shift into the different rows the value of the matrix A, and into the columns the value of the matrix B. And at every clock cycle, we do a computation. and at the end of the computation, we have the results stored in each processing element. So it means that basically we cut down the complexity of the matrix-to-matrix multiplication down to up to a linear complexity. So this is why systolic arrays are very well used in the AI world. And a similar consideration can be done for the case of the GPU. Now, the point is that if you inject a fault into the memory, for example, here we change this value here, so from 3 we go to 4, we do the computation, we get this wrong result. But if we inject into the hardware, and in this specific case into the systolic array, we may have a different behavior. And if you can see, this was what we obtained by injecting in software versus what we obtain when we inject into the hardware. So this is just an example showing why it is important to consider the hardware. But again, if we go down to the hardware, we have to spend more time. So it is always a trade-off. So hardware is important, and what we can do with the hardware. So for example, if we still consider the systolic array, we can try to understand if the way we design the data path has an impact on the dependability. So in systolic array, we can change the type of the data path. Here we have 3 examples. Sorry. In this experiment, what we did was perform injection in the different data path and see what happened when in 3 different applications. What happened concerning critical, safe, and masked. So for example, here you can see that the output stationary data path is the one showing the lowest number of critical fault. So if I have to go for a more dependable implementation, I can, by design, start to analyze what is the more robust. Here I don't introduce any extra mechanism to compensate faults. I simply check what happened by design. So this is one important. Then, still coming back to the fault injection, I would like to reduce the fault injection time while keeping a precision high, so while keeping the simulation low. And I have 2 possibilities to do that. One is to reduce the number of faults to inject, and the other is to reduce the amount of inputs that I will process, right? The workload. So concerning the faults, there are already works that tell you how many faults you should inject in order to have a statistical significant evaluation of the dependability. So look at this example. So basically here we have what? We have 2 models. So the application is 2 different models, ResNet 20 and MobileNet. The fault model is permanent fault, in this case, impacting weights of the model. The fault injector was a modified version of the PyTorch FI. And we simply classify the faults as critical or non-critical. Now, if we consider all the possible faults, we have to inject 70K faults or 151K faults, depending on the model. To compute this, we simply consider how many weights we have and how many bits per weight. But we can do what is called statistical fault injector. And basically here we can simply random select subset of faults in order to achieve a certain precision. So here we have 99% of confidence that by using this number of faults, I have statistical significant evaluation. So if I do this, I can reduce, in this case, 10 times, for example, the number of faults to be injected. But I can do even more. I can use the data-aware statistical fault injection. And in this specific case, data-aware means that I implicitly consider the data representation used by my models. So let's consider the 32-bit floating points. Injecting faults into the LS bits of the mantissa will have a very small impact compared to injective faults into the exponent. So this is another criteria that you can use to further reduce fault injection, because you only consider faults that have higher probability to lead to a critical situation. And if we do that, we can reduce much more the number of faults to be injected. So here you can reduce almost 3 orders of magnitude the injection time, because you reduce 3 orders of magnitude the number of faults to be injected. On the other hand, you can also play with the workload. So how the assessment is done. You have an image classifier, you have a data set, you apply all the images of the data set. Here, for example, the data set is CIFAR10, sorry, and basically is composed of 10,000 images. So if I randomly apply these 10,000 images, I detect some faults, and this is the curve of the critical fault. So you can see that at the end we saturate at this number, and this is the number of critical faults that I can observe when I use this data set on this specific model, when the injection is done by injecting 16K faults. This number 16K faults is very close to this one. Yeah, because we want to do a very precise fault injection. Now, but can we only use a subset of these 10K images? So, for example, we can try to rank the input images following some criteria. We can use, for example, distance matrices. We can use cross entropy loss. We can use Gini index. We have the knowledge of the probability. So we have a lot of internal metrics. And basically, depending on which metric we use, we can rank the images in such a way that basically you can see that by simply applying almost 1,000 images instead of 10K, I reach immediately the number of critical faults that I detect, right? So this is very important, because it means that I can significantly reduce the number of images that I have to apply during the fault injection to achieve a meaningful dependability evaluation. So if I play with the two variables, number of faults and number of inputs that I apply, I can reduce, and I can still use my fault injection. Another point is neural networks are very vast, so it's also hard to compare fault injection outcomes, because depending on where I pick the model, I can have different, let's say, results, etc. So one of the points we worked was to the definition of a benchmark suite for exactly the CNN dependability investigation. Just to tell you an example, so let's suppose that we still fix the model and the data set, and we fix also the same number of faults, right? Now, this model can be trained by using different parameters, and different trainings lead to clearly different accuracy. This is something understandable, but they also lead to different, let's say, impact on the dependability. You can see the difference in percentage of the masked and also in the critical fault. So the point is that when I do fault injection on my model, on which model I should compare with. And this is not really easy, because depending on the model, I can compare different things. So what we did was the definition of this benchmark suite. And if you are interested in, you have the paper, and you have the link to the GitHub repository. And this is a work that we did in collaboration with Politecnico di Milano and Torino. So basically what we do was to divide by platform, so PyTorch or TensorFlow. We use GPU as a hardware target. The task were image classification and segmentation. We have some data set that are represented in floating point 32 and different models. So here, from here, what you can download is the model. You can download the fault list. You can download all the weights, because all the mods are already trained. We share also all the training options, so you can redo the training yourself. and then you can compare your own techniques with the data that we get here, right? So those data are not particularly important, but it's simply to say that you have something on which you can compare because you have everything that is released. So the code source, the data set, etc., etc. So this is something that is important for the community. Then once you know how to say, you evaluate your dependability. So you know where are the critical elements. You want to introduce countermeasures. So you want to increase the dependability. You want to make your AI system more robust. And this came by using, once again, very well-known technique like redundancy. That could be structural redundancy. So you triplicate a given component, could be hardware, could be software, etc., and then you both. You can add correction codes, so you extend your data representation by adding detection of code correction codes. But since you do this, it means that you increase the overhead of your AI system. And the critical point is clearly to understand how much is the risk in order to design a proper safe mechanism. So here you underestimate your risk. Right? The problem is that we cannot apply classical fault tolerance mechanisms to AI because AI models, you can see here, grows very, very fast, while the hardware grows very, very low compared to this. And you cannot simply triplicate a model. You cannot triplicate the hardware because it's very, very costly. So there are a lot of works targeting what is called AI-aware fault tolerance. And I will show you some example in the last more or less 10 minutes of the presentation. So all these techniques basically are based on the hypothesis that the network itself, the model, or better, sorry, the AI system, is able to tolerate a certain amount of faults. This is a concept that you already saw in the very first example, in which we have a masked situation, no difference. We have a critical situation, a very big difference between the faulty and the fault-free execution, and something that is different but still usable, what you define as safe situation. So it means that somehow there are some inherent mechanisms. I also show an example in which, depending on the data path of a given systolic array, I have different figures of critical faults, right? So this is the main idea behind the AI-aware fault tolerance mechanism. So let me start by the first example. So this is what I call specifically graceful degradation, because first of all, from the hardware point of view, we target systolic arrays. So all these M blocks are MAC unit, the processing elements. The red elements are the faulty ones. So here the idea is to, when we have a faulty element, to bypass the faulty element. We can introduce multiplexer. So basically here, we skip this one and we go directly to the next. So from the software point of view, is like we set at 0 the contribution of this element here, here, and here. So this is like we apply what is called in AI the pruning of a network. So we set at 0 some components, some parameters, because these, from the pruning side, help in reducing the memory footprint without impacting the accuracy. So you can see here what happened when we have this number of faulty elements. So you can see that in these two cases, if we look at the blue curve, you have a slightly degradation of the accuracy. And basically for the two cases, we can tolerate, let's say, up to almost 12% of faulty MAC unit here. The red one, on the opposite, is the same technique in which we do some fine tuning, or we do basically another train step. What is the idea? The idea is that if I know the failure bitmap here, I know where are the faulty MAC. I can basically do a training step in which I inject those faulty elements, and basically I modify the parameters of the network in order to compensate the presence of those faulty elements. And if we do that, you can see the red curves here that almost are constant. So we don't have any significant impact on the accuracy. So the network maintains the same performances than the original one, so the faulty-free one. So, and if you look at the chart, we can tolerate up to 50% of faulty memory units, right? So this is an interesting result. And we don't have any extra hardware. The only extra hardware are the multiplexer to bypass or not. Then I don't talk about how we can determine if this element is faulty or not. This is another story. But if we know this, by using a multiplexer, we have this, let's say, fault tolerance technique. Another technique is, let's say, the idea is similar, but is applied at a different level. So this one is related to error correction code. So let me just briefly show the idea. What you have here is what? This is the weight, so the parameters of the models. Here, the parameters are stored as integer data represented using 8 bits. More significant bit, less significant bit. So you have 0 and 1s. So the white blocks are 0, the gray ones are 1s. Now, the point is that the idea is to, instead of adding error correction code that is costly, why don't use parity bit? So we use the LS bit as a parity bit. And in the case we detect a fault, so because the parity is not correct, we can correct the complete weight by simply putting the weight at 0. So the correction is setting at 0 the faulty weight that we just read from the memory. Again, this is like doing pruning. So we come back to the concept of before, right? So again, we can tolerate a certain amount of weights set to 0. So here you can see some results, and those are interesting because here the results are related to these two models, MobileNet and SqueezeNet. And there are different data types. So here we have integer 8, brain float 16, and floating point 13. And the different colors are the following. So either we do not apply this technique, so there are no fault tolerance mechanisms, or we can apply the technique at different granularity. So we can actually protect every weight. So every row in this matrix is protected by this parity code, or we can protect blocks of bits. So 1/64. So every 64 bits we have this protection. Every 256 we have this protection. Now, if you look at these, the floating point results, 1, 2, and 3, you can see that basically without this technique, we have a drop of the accuracy that occurs very soon. As soon as we have some faults, we have a drop in the accuracy. But if you apply our technique, depending on the granularity, basically we maintain the accuracy almost equal to the original one, until a certain level that corresponds to when the number of zeros is too much and basically the performances, so the accuracy is reduced. So depending, clearly, if we protect everything, we obtain the highest accuracy at the higher cost. Here. But the interesting point is this one. Here we have the same network, MobileNet. We have integer 8-bit. And for this specific one, indeed, the most reliable solution is to do not apply opportunistic parity. And this is something very interesting because it means that basically the network is more robust if I don't do nothing. Why this? First of all, it depends on the data type. And here we already lose one of the bit because we use it as a parity bit. So we have already something that is impact the accuracy of the network. And for this specific case, it doesn't work But you can see in the paper that also for the other networks with integer 8, we have a better dependability if we do not apply this technique. So this means that AI-aware fault tolerance works under the specific conditions. So it's very difficult to generalize. And this is another characteristic of the AI systems. Now let me go to the end because time is running fast. Sorry. So the last one is timing redundancy. So similar to the classical timing redundancy, the idea is to perform a check, and in the case we have something wrong, recompute the computation. Now here the idea is to introduce the check at the very beginning of the model in order to avoid to compute all the inference and then check only the outputs. If we detect very early the occurrence of the fault, we can simply recompute the first layer. So we save time in a sense. The problem is which metric should we observe, compute? So in our experiments, we worked on the output feature map. So basically the output of this specific layer. And we get the max value, the mean value, or the sum of all the values. And what we do a kind of profiling. And basically, depending on the profiling, we can say that some values are very unlikely to arrive. So if you observe one of these unlikely value, we can somehow trigger a kind of warning and say, look, I observed the output of this value, of this layer, sorry, and what I got is very unlikely to be observed, so it may be due a fault. So do the recomputation, and if it is a transient fault, the next computation simply correct whatever. Clearly here you can have true positive, false negative, etc. So the idea is to maximize the true positive in the case of critical faults, right? So I want to maximize the number of early detection correctly activated, and I want to minimize the early detection that you do not activate, because this will lead to a critical fault, so a situation that I want to avoid. You can also have the other case in which, for the case of non-critical faults, you want to minimize the false positive. So you don't want to activate this if it is a non-critical fault, because at the end of the story, the impact is not important. But you want to maximize the error early detection correctly not activated. So you want to do not, so the true negative, you want to do not recompute if you don't have to. So we did some results on two models. We set up the threshold, and the interesting point is that different metrics can lead to different results, because for this network, since I want to remember, I want to maximize and minimize the different values. So those are the best solution, the green ones. And for this network, to obtain for the critical faults the best solution, I need to use the tensor max metric, while for the non-critical faults, I have to use the tensor sum. So two different metrics. This means that I have to complexify the design in order to take into account the two metrics. And most important, for this other model, with the same one, I can basically obtain the best in the two worlds. So again, if I change model, I have to redo the analysis. So I have to redo the fault injection. And this is why I stressed a lot in the presentation about the importance of the fault injection, because every model is somehow different from the others. And clearly, you have to consider also the data set, and these can lead to different dependability results. So you have to take care of this, and you have to take care of this because you want to design the best AI fault tolerance approach for your specific system. So this leads me to the end, and just some conclusions. So the main goal is that even if you have a perfect model, this one is deployed on an hardware, and hardware faults can jeopardize the execution. So you can have problems. You must take into account this. So you need to evaluate the impacts of faults. So this is a costly operation. You have to identify techniques to speed up it. And this is because you need design space exploration, because if you change a model, you may have different dependability outcomes. That means different contour measures to be implemented. Another point is that is something that is coming, but what happened during the training? And during the training, can we somehow take into account faults? So already exists fault-aware training, is a very well-known technique, but again, it requires fault injection campaigns that are a long campaign. So there are a lot of things to do in this specific field in all the show that I present. And let me conclude by saying a big thanks to the team in Lyon. So this is a picture with my colleagues and the PhD students that collaborate directly on what help me and collaborate with me. And since I have just 1 minute more, remember that next year we will have date 2026 in Verona. Now it's too late. We just concluded the submission, but you are still in time to register to the conference to attend the venue. And if you submit the paper, I really hope that we will meet together in Verona next year. So with this, thanks a lot, and I'm open to questions. And clearly, you are free to contact me by email if you want to discuss with me later on. Thanks a lot.
Okay, thank you, Alberto. Very impressive talk. Yeah, I did not. Yeah, I saw you would just talk about the basic trustworthy AI, but you talk about you've perfectly coined this fault injection and also the fault tolerance into this AI computing and the hardware. I think it's very impressive. Okay, great. We have a couple questions. I think you can look at the Q&A boxes. Okay.
Yes, let me open a Q&A. Okay, see.
Yes.
Okay, so I start. Can you open a workshop with a submission deadline in October? This is is not only depending on me. There will be workshops, so keep simply monitor the date websites. So let me. I don't know the order. Maybe I try to proceed in the from the last question to the new one. Would be okay for you?
Yeah,
I see
I think
that
so. Yeah.
Giovanni. Okay, maybe I jump. Giovanni, you have a lot of questions, so I will do one of your and one of Shu. So just to anyway. So question of Giovanni, slide 50. When testing for critical faults and non-critical faults, why do we need to evaluate for all of the following three metrics: tensor max, tensor mean, and tensor sum? So the point is that what we do exactly. So slide 50 is this. So here we tested all the different metrics, each one with a given threshold. So for example, this means that for us, the maximum value that we expect is 9. So if we get something higher than 9, we suspect that is a fault. So to obtain this value, we do indeed a fault injection. So actually, we do fault injection with all the faults. So first of all, we characterize the faults in critical and non-critical. And then for each fault, we see how many times the fault activated or not the threshold. And depending on the criticality or not the criticality, we can determine if it was a true negative, a false negative, a false positive, a true. And we do that every time. So yes, we need to run the complete fault injection. You let me know if the question is answered in a correct way or you need more details. So now I go back to a question from Shu Oren. So hello, when it comes to trustworthy AI, should we treat LLMs differently for non-LLM AI systems? In other words, is there a paradigm shift in how we approach trustworthiness between LLM and traditional AI? So there are works now targeting transformers and LLM in general. And basically, there is one fundamental difference. It's not only the complexity, because first of all, LLMs are much more complex in terms of number of parameters, etc. But one point is the accuracy metric. So when you have a classifier, it's quite easy to determine the accuracy. Either the input is correctly classified or not. But when you have an LLM, you need a measure to determine the quality of the generated text, if it is a text generator, or the quality of, for example, a translation if the LLM is to translate from one language to another. And once you have the metric, you can actually run the fault injection and check the impact on this metric. So the very first, the very big problem, in my opinion, is first of all to understand how to measure the quality of generated text. If we talk about generative AI, and I don't have that, but I see this as the problem. So every task executed by a given model needs a proper metric to be evaluated, right? And concerning the other point is the scalability, because bigger the model, clearly more complex the fault injection. You have to implement very smart techniques to run the fault injection to take into account the complexity. The scalability is the issue. I come back to the question of thanks to you. The question of Giovanni. So slide 46. So Giovanni has a lot of specific questions. Slide 47. 47. This one. It seems that about mobile net uses integer of weights for. Sorry. It seems that about mobile net uses integer representation of weights for the deep neural network instead of floating-point representation like the other deep neural networks such as QuizNet. So here indeed, this is just a screenshot from the paper, and there are three networks that are used, and for each network there are 3 data representations: integer 8, floating point 32, and brain float 16. So, and the results are somehow really dependent on the data type. So it's not that MobileNet is the only one that using the inter-array bit in this specific screenshot yet, but if you had a look at the paper, all the data type of these 3 data types are used in the evaluation. Slide 46, still a question from Giovanni. Isn't the graceful degradation that is enhanced with the training steps similar to copying the fault from the faulty deep learning model to the new deep learning model? So if I understand the question is, so yes, first of all, yes, we do a training. So we talk about this slide. So the difference between the blue and the red curve. So we do this extra training step, copying the fault from the faulty deep. Yes. So somehow we have. So the idea is that you have this faulty bitmap. So somehow you have a test procedure that can tell you which are the faulty MEC units. So you can extract this information from your hardware, and then let's say, for example, in the cloud, you can do a training injecting the information of the faulty MEC. And so you can actually adjust your model and then deploy back the model on your hardware and obtaining this enhancement in the graceful degradation capability to correct. Slide 42. 42 is this one. Is there an update benchmark suite for open source foundation model? So not yet, but basically one of the idea of this benchmark suite is that is open, in the sense that if some of you would like to add his own AI model with dataset, is absolutely possible. You simply have to contact us, and then you must be aware, let's say, available to share the code and the data in order to let the other users to do experiments in the same condition. So yes, it's possible to extend. For the moment, we don't have any LLMs, but if you would like, if you have this and if you like to share with the community, you are very welcome. Every one of you are very welcome to contact us and to act in this case. I go back. So again, Giovanni, let me see if there are other. Okay. I go back. So there is slide. No. Another question is, can the SMT solver based ATPG be exploited to inject faults in deep learning models to test for their trustworthiness? Could be. I don't know. It could be. I don't know. This is something that I personally don't do. So it could be. So good point. And maybe we can discuss in offline if you want to have more exchange on this. Slide 16, is there a way to use, so all the questions related to SAT solver, and so I don't know. I think it is a very good point, and maybe I'm also interested in discussing with this. Maybe Giovanni, you can really contact me. Slide 13, can we exploit faults in the manufactured die of the IC for responding weakness in the trustworthy AI? Well, yes, but you have to know what are the faults. What are the faults? So it's not. So it means that you are, as an external, should retrieve information about the status of the chip and then exploit internal vulnerabilities due to the faults in order to perform attacks. Theoretically speaking, it's possible, but you have this information that you have to retrieve somehow. So, and again, I'm not an expert in security, so I cannot tell you more than this. But in principle, yes. If you know a specific vulnerability because you know that some component is faulty, you can actually use this as vulnerability point to perform it. And if there are other questions, so there is one. LLM-based HDL source code generation can be evaluated since classical traditional data. Yes, for example, this. So this is a way to compare what the quality of the answer. Yes. From slide 42, can we update the benchmark suite with deep learning model for ML commons? Same answer that general LLM. We don't have this yet. You are very welcome to suggest new models to provide you.
Okay. Yeah, Alberto, I think we have a last question from the chat box. From Sardine. Okay. Can you take a look at what is the likelihood of bit flip that one?
Where is the question? I didn't get it. Is in the chat?
In the chat, yeah.
Sorry, I was looking at the question in Q&A.
No problem. I think this is only one here. Yeah.
Okay. What is the likelihood of bit flip in hardware, and what will happen if the faults hit the control path and the data path? So, very excellent question. So, for the likelihood of the bit flip, well, this depends on the source of the bit flip. So, if you consider the impacts of radiations, these you have the literature. So this depends, for example, on if you are at ground level or at the altitude. So you have statistics on this. There are public. Depending on the other source of fault or of defects, everyone can have consequences. So it depends on but the probability is not negligible. This is the point. And what happens if you hit the control path? This clearly can completely compromise your execution, like in a general microprocessor. So if you hit the control path, you may have a very problematic situation. So there are some papers, not a lot of them, that basically analyzed the impact of faults in the control path of neural network. I didn't talk about this, it's true, because I didn't work on that specifically. So the control path, let's say dependability, but this is also another important field that should be investigated. Yes.
Yeah. Okay. I think that's it. I think that people are very interested for your topics. That's good. Yeah. So I think Alberto already mentioned if you have further questions, you can email him. Yeah.
Absolutely.
And of course, welcome everyone to register the DET conference, and you can talk to Alberto in person in Verona. That would be even nice. Okay. Yeah.
Absolutely.
So thanks everything. Yeah. Thanks for the great talk for today. Okay. Thank you, Alberto. Yep.
Thanks to you, and have a good day, morning, afternoon, etc. Bye bye.
Thank you. Bye bye.